Okay, so what did you discover when you tried to graph this? So x cubed plus x squared. I'm going to factor out the x squared, and that leaves me with x plus 1. That lets me know that this graph has an x-intercept at -1 and at 0, and that 0 is a multiplicity of 2. We're going back to 30-1 graphing here. So I have a -1 and a 0. So I would know he has a positive leading coefficient. So he starts down in quadrant 3, goes through the -1, comes back up, and just bounces off of the 0. Okay, and then I am graphing y equals 2x. So that's got a bit of a steep curve to it. It's not going to be perfect, but I know he has an x-intercept of 0 as well. So something like this. And this is a little tricky because there's a tiny little region in here. And then we have this big region. So we end up with 2 pieces. So find the total area enclosed. So it is enclosed. It's not like the previous question where it was just a space between 2 functions. This one is totally enclosed. So what that means is that I need to figure out what these intersections are. Now the one in the middle is easy. That's 0, 0. But those are going to be my boundaries. Those are going to be my A and B. And in this case, we have a second, we have 3 of them, so we almost have a C per se. But we actually have to do this in 2 chunks. We have to do a region 1 and a region 2. So if I look at region 1 being here, then region 2 is this little piece in the second section. Okay, so let's think about what those intersections are. Okay, let's find those intersection points. Because we switch between who's upper and who's lower between the regions. So we'll look at that in the second part after we figure out the intersections. So I know the middle one is 0, 0. But what about those other ones? So we actually have to think about back to like grade 11 math. Where do those happen? They happen when the 2 functions are equal to each other. So when the first function and the second function equal each other, then we can find the intersection. So when does x cubed plus x squared equal to 2x? And then we go ahead and solve that. So we'll move the 2x to the left, make it equal to 0. And then we would factor out an x, and that would leave me with x squared plus x minus 2. And then that would factor to x plus 2, x minus 1. And then we see that our x-intercepts are happening at x equals 0, -2, and +1. So I now know this lower boundary on the left is at -2. And the upper one is at 1. And I only need to know the x values. I don't actually need to know what the y values are. So that's great. Now I know my boundaries. Okay, so then we're going to look at this in 2 different regions. So let's look at region 1 to start with. Okay, in region 1, now I didn't label my graphs. Tisk, tisk, Malmstrom. Okay, so this is y equals 2x. And then this other one is y equals x cubed plus x squared. Okay, so in region 1, the upper boundary, the upper curve, is y equals x cubed plus x squared. Okay, so upper is x cubed plus x squared, which means the lower is the 2x. And so when you go upper minus lower, you get x cubed plus x squared minus 2x. And that is between -2 and 0. Okay, and then region 2, what happens in region 2 is the upper boundary is actually the y equals 2x. So they switch spots, okay? So let's look at that. Region 2, we have the upper as 2x and the lower as x cubed plus x squared. So be careful when you subtract here. Upper minus lower, you get 2x subtract x cubed plus x squared, which is 2x minus x cubed minus x squared. Okay, so those are our two regions. And now we're going to calculate the area. Okay, so the area of the entire question, the furthest right boundary on this is 1. So this is equal to the first region, and the first region goes from -2 to 0 of my first region's function, which was x cubed plus x squared minus 2x dx. Plus, we're going to add it to the second region's area, okay, which goes from 0 to +1, and the second region is 2x minus x cubed minus x squared dx. Okay, so this is region 1, and then we're going to add it to region 2. We have to do it in 2 separate chunks. All right, I gave myself some extra room. Let's see if I can read this. So when we go to evaluate this, we get the antiderivative of x cubed is 1/4 x to the 4th plus the antiderivative of x squared, 1/3 x cubed, minus 2x squared on 2. That's the first regions, and that one gets evaluated from -2 to 0. And then let's do the second region. So the antiderivative of 2x is 2x squared on 2 minus 1/4 x to the 4th minus 1/3 x cubed, and this one's being evaluated from 0 to 1. Okay, so here's where there's a lot of having to substitute stuff in. Make sure you put them in the right order. If I put 0 in this first function, I get 0, 0, 0. So I'm going to get a 0 just to not have to write out so much stuff. Subtract when I put in the -2. Okay, so this is region 1. 1/4 -2 to the 4th, make sure you have this in bracket, plus 1/3 -2 cubed minus those 2's cancel, -2 squared, plus region 2. Okay, so those 2's cancel. And 1 is the first number I'm going to put in because it's the bigger one. So 1 squared minus 1/4 1 to the 4th minus 1/3 1 cubed. Again, if I put in a 0 for each of those x's, I'm going to get a 0. So subtract 0. So what do we get? For the first region, we get, when we put that in very carefully to our calculator, we get that that's equal to 8/3. And then the second region, when we're very careful to put that in, we get 5/12. And then when we add that all together with common denominator, we get 37/12 units squared. Okay, so when you are doing this and you have an intersection of your graphs, okay, you have to look at it as 2 separate regions. You really need to pay attention to where those intersection points happen to find your boundaries, because in this question, the intersections between the 2 curves became my boundaries to my graph. And then look at the 2 regions separately. Okay, and then within each region, you do need to integrate. Okay, and then you add those 2 areas together, and it gives you the total area that was enclosed. All right, what's the next question? Ooh, we have a sine and a cosine graph between 0 and pi. Okay, so again, I'm going to pause the video here. I'm going to come back in video number 3, see how your graph is. Okay, so really be careful about how you graph your sine and your cosine graphs. Okay, it's really important. Give yourself a scale, maybe count in 45-degree increments or 90-degree increments, something that's giving you some accuracy so you know where your graphs are intersecting. Okay, all right, I'll be back in video.